Let's talk about program optimization. So by way of introduction, we're going to look at some motivation for doing this and talk a little bit about what optimizing compilers can and can't do. We've been mentioning throughout this semester that there's more to performance than just asymptotic complexity. We know that asymptotic complexity is still going to be very important. You got to choose the right algorithm with the right level of big O complexity, but there's more to performance than just that. In fact, we can see constant factors having an impact on our performance by as much as a 10-to-1 ratio. So we want to optimize our various algorithms, we want to optimize data structures, we want to optimize procedures and procedure calling, we want to optimize loops. All those kinds of things are implementation details in some sense of a particular algorithm itself, but they all can contribute to making our programs go faster. We do want to know what's under the hood in order to optimize their performance. And a lot of what we've talked about this term has focused on some of those issues. So we've discussed how the program is compiled, how it gets converted from source code to assembly language to machine code, and then loaded into the memory and executed. We've talked a lot about how the processor itself operates, how memory operates, what the memory hierarchy looks like. So I'd like to know how we can measure performance, how can we characterize the behavior of a particular algorithm, and then how do we improve that performance without clobbering the modularity and generality of our code. We don't want to go to such an extreme that we lose the ability to maintain our code or to employ good software engineering practices purely in the name of performance. There may be some places where it's necessary to trade off performance with maintainability and complexity of the code, but it turns out that those cases are relatively few and far between. We know that we're using very fancy compiler technology, and any modern compiler, including GCC or any other commercial compiler, is going to do a whole bunch of optimization in order to map that program that we create into something that is going to be executed well on the underlying hardware. So some things that an optimizing compiler will do are things like register allocation, figuring out what goes into registers and what should stay out of the register. So for example, in a for statement, the loop index in our for loop is going to be accessed a bunch of times, and the compiler will probably try to put that in a register. But there's a fixed number of registers available, as we're aware. So at some point, the compiler has to make choices about whether it's going to put a particular variable in a register or if it's going to leave it in an ordinary memory location. So that allocation process is quite complex, but it has a big impact on the behavior of the code. The compiler also is going to take a look at how does it compile various constructs in the source language into the target assembly language. When we were discussing things like how does the compiler convert different kind of looping constructs, jump to the middle, those types of things, we explored some different ways that the compiler could choose to convert the code from one form into another. And that's another part of the optimization process, trying to look at the structure of the code and make choices about how to compile the code into assembly language. Another thing that the optimizing compiler will do is what's called dead code elimination on the contents of a procedure, for example, and coming to the conclusion that there might be some code that's in there that can never be executed. If there's cases or conditionals and so forth that the compiler can prove will not allow certain parts of the code to run, it might throw that dead code away. And it might also look for minor kinds of inconsistencies, for example, choosing to switch around the sense of a test or something like that that might allow it to generate assembly language that will run more efficiently than if it does kind of the obvious trivial conversion. Compilers, although they are going to try to do these relatively small optimizations within functions and so forth, they don't normally improve asymptotic efficiency. They're not going to choose a different algorithm. They're not even going to be able to recognize the algorithm that you're using. So that's still on us. We have to choose the best algorithm. And again, the big O savings are going to be more important in the larger scheme of things than the kinds of optimizations that even the fanciest compiler can come up with. But again, we're trying to figure out how do we reduce these constant factors within the asymptotic complexity that are going to give us better performance than if we ignore those constraints. One of the things that we can do to help the compiler optimize in the ways that we've been describing is to avoid things that we're going to refer to as optimization blockers. These are things that we can do in our program, usually unintentionally, that are going to prevent the compiler from employing the kinds of optimizations that we've been discussing. And we're going to look at two examples of that, memory aliasing and side effects. We also want to be aware of limitations of optimizing compilers. Fundamentally, the fundamental constraint here is that the compiler cannot change the behavior of the program. So if we code in a certain way in the source language, the compiler has to be very strict about following the instructions that we're giving it in the source code and making it operate exactly the appropriate way for that language that we're compiling in the assembly language. And this is going to be true even if the optimization that the compiler could choose to do would cause problems only under very, very rare conditions. The compiler is going to be very careful to generate code that will work in every single possible case of input or control flow or anything like that in order to avoid changing the way the algorithm is operating. Another thing to keep in mind that is a limitation for a compiler is that most of the analysis that it does, for example, dead code elimination and register allocation and so forth, most of that analysis is going to be done only inside of procedures. So within a C language source file, within a single function, that's going to be kind of the boundary that's placed around where the compiler is going to do optimization. It's going to look at one function at a time and try to come up with an optimal way to compile just that function, without looking at the interaction that that function has with other functions. So many compilers will stop right there. GCC actually does a little bit more than that. It will look for optimizations between functions or procedures, but it'll only do that in the same source file. So if you've got 10 functions in a particular source file and they're interoperating with each other in various ways, GCC will try to do analysis to do optimization of the way one of those procedures calls another, for example, but it won't look outside the boundary of a single source file. So if you got 1,000 source files in a project, the optimization is going to take place only within each of those files, not across them or between them. The other thing to keep in mind is that most of this analysis is done purely on static information. When the compiler is inspecting your source code, all it has to go on is basically the structure of the code, the structure of the generated assembly, the way that data move back and forth between registers and so forth. And it's going to only make assumptions that it can make without any regard for the actual data that's going to be processed by that function. It's just too hard to anticipate the runtime inputs that are going to show up in order to try to predict how that algorithm is going to behave under various conditions. So it's only going to look at things that it can optimize or prove based on the static structure of your code. And then the final limitation here is that when in doubt, the compiler needs to just be really conservative. It's going to try to make sure that no matter what the input is, no matter how goofy our code is structured, that it follows very specifically exactly what we ask it to do in the source code, and that it's going to work under any kind of condition, no matter how things are called or what kind of input's showing up. It's got to be conservative so that it's first of all correct and then performant. Let's take a look at a couple of optimization blockers. Remember, these are things that we can do in our code that will prohibit the compiler from making optimizations because it's concerned about correctness first and then performance second. Here's an example of a couple of little functions. They both take the same argument list, a pointer to along and another pointer to along. And what they do internally is basically add the value at the second pointer to the value at the first and do that twice. So in twiddle1 here, we're saying go get the value at yp and add it to whatever's at xp, and then do that again. Take the value from yp and add it to xp. The second case looks like it should do exactly the same thing. It's going to take the value at yp and then double it and then add that to xp. A simple analysis would suggest that these functions should do exactly the same thing. And in most cases, they will do the same things. However, there are cases where they will differ in their behavior. So let's look at a way that we could call this. Here's a driver function, a main function, and it's defining a long called x and assigning it to a value of 5. And then it calls twiddle1, and it passes a pointer to it, the same long variable for both of the arguments. Now, it may not have been the intention of whomever wrote these twiddle functions to cope with the case that xp and yp might point to the same location in memory. It kind of doesn't feel like the intention of these things. The idea looks like it's trying to go grab one value, double it, and add it to another value. But the fact that it's been implemented in this way means that it's possible for both of those values, both of those pointers, to point to the same thing. And that's what's happening here in the way it's being invoked. We can see here that twiddle1 is going to print out x equals such and so. And over here in the output from this thing, we'll see that the twiddle1 produces x equals 20 when it's done. Now we're going to go ahead and reinitialize x back to 5, and we're going to call twiddle2 in the same way. Pass the address of that variable x in both arguments of twiddle2. And if you look at the output from twiddle2, we can see that it's a different value that comes back. Now, if we call either of these twiddle functions with xp and yp being different addresses, they will both work identically. But in this case, we've got what's called aliasing. We're passing the same underlying value, this variable x, as both arguments of that function. When we call twiddle1, what happens is we get xp incremented by what's at yp. Well, to start out with, xp is 5, and what's at xp is 5, and what's at yp is 5. So the first statement here results in 10 being stored in xp. And then we do the same thing again, except yp now points to a value that has 10 in it and adds that to the existing 10 in the same location, which is why we get as our output a 20 for twiddle1. On the other hand, for twiddle2, we're taking the value 5 that we passed in at yp, doubling it to 10, and adding that to the existing value 5 at xp, which is in the same location as yp, and we end up with the value of 15. So although we might not be thinking when we code these kinds of routines what's going to happen if xp and yp point to the same thing, the compiler is going to have to pay attention to that possibility, and as such, it's not going to be able to do any optimization, for example, to convert twiddle1 into twiddle2 in order to presumably save some execution time, because it's going to end up with a wrong answer. Let's take a look at another optimization blocker, this time involving a side effect. So we've got a function, or two functions here, func1 and func2, and they're both going to call an underlying function called f. I've got a forward declaration here so that the compiler's happy with that invocation. And we can see here in func1 that what we're going to do is call f, and call f again, and call f a third time, and call it a fourth time, and add up all of those values that were returned by f, and return that as a value from our function. So you might look at that and say, well, f is going to return the same thing in every case, and we're going to call it 4 times, so that would be equivalent to just calling it once and multiplying it by 4. Well, if f was a pure function, in other words, if we got the same value back from f for the same input from f, that would actually be a legitimate assumption. But again, the compiler can't assume that about f. In particular, it's possible that f itself is declared in another file. That's the reason that I needed to have this forward declaration at the beginning. And as I said before, most compilers will only look inside of individual functions, and even GCC will only look within the same file. So if I have a different file where f is compiled, the compiler can't make any assumptions about what f is going to do. Let's look at an example of the driver function here that's going to call our func1 and func2. And here's the definition that we're using for f. So again, this is a separate file, so the compiler has no knowledge when it's compiling over here what f is actually going to be. And as the name of this optimization blocker implies, this thing has a side effect. So in the driver code, we've got this counter variable. The function f is going to grab the value of that counter variable, and that's what it's going to return to its caller, and then it's going to post increment it. So the next time that f gets called, it's going to return something different. We're going to then, in our main function, initialize the counter to 0, call func1, and then print out the value of the counter. You can see here from the output that the first example here returned a value that said that the counter was 4. And then we're going to reinitialize the counter to 0, call func2, and do the same thing. And you can see that in that case, we get a different result where the counter has a value of 1. Now that illustrates very clearly that these two invocations don't produce the same results, and the reason is that when we call f itself 4 different times, we're actually going to increment the counter 4 different times. So we're going to end up with a different value in the counter at the end of the process than if in function 2 we only call the function once, which is going to increment it from 0 to 1, and then we're going to return 4 times that value, which means that we're going to get 4 times 1, which is just 1. Again, it might seem to us like these two things are equivalent. And if we were trying to compile function 1, we might say to ourselves, well, we're just calling this thing 4 different times and then adding the results. Let's optimize that. We can turn it into a single function call. We know function calls are relatively expensive now because we know what's going on under the hood with pushing and popping and parameters and all that stuff. And then we can multiply it by 4 by just shifting 2 positions. So it seems like we could make this thing a lot more efficient. But again, the compiler is going to be more concerned about correctness than performance. And these two functions do different things under different conditions depending on how the f function itself is defined. And the compiler is not going to make any assumptions about what f does and generate code that will work no matter how weird f is itself. Let's turn our attention to how we might express the performance of different implementations of the same algorithm. An obvious way to talk about performance is to just talk about the amount of time it takes for a particular function to run. There's a lot of challenges associated with doing it that way, though, because we might run it on a different computer that has a different clock speed or a different operating system or a different mix of other processes that are running on that machine. So it's a little dodgy, a little CPU specific to be able to try to measure things just according to the wall clock time. An alternative to that is to think about something called cycles per element. By a cycle, what we mean here is basically just a tick of the CPU's clock. And because we're thinking about just sort of how many ticks or how many instructions are going to be executed in order to arrive at a particular result, we've kind of taken the clock speed itself out of the picture. Whether the clock is running at 1.5 gigs or at 2 gig, there's probably going to be about the same number of instructions executed from one machine to the next to the next. So that tells us kind of how much work we're going to do per element. And when we're thinking about an element, we're usually thinking about, it's kind of like the n in order n calculations. We're sort of thinking about the size of the problem. So we're going to look at some examples that involve doing operations on an array. And in that case, each of the elements is just an element of the array. So CPE, cycles per element, is saying how many cycles are we going to have tick by for each of the elements of the data that we're trying to process. We can get after this CPE by just conducting some experiments. So we're going to run our implementations for various problem sizes and measure how long they take to execute. Here's an example where I'm basically just summing up the elements of an array. I've got 2 different algorithms called psum1 and psum2, and the points on this graph just correspond to the runtime for different size problems. Here's the number of elements on the x-axis and the number of cycles on the y-axis. And after running those experiments, we can do a least squares fit. So we're just calculating the parameters for y equals mx plus b, and we can interpret that in terms of the behavior of the algorithm. You can see that both of these algorithms have a y-intercept that's about the same, and what that timing represents is really just kind of the setup time for the algorithm, the processing that needs to get done in order to get to the first actual sum calculation as we're moving through the array. And then the slope of the line basically has to do with how many cycles we're going to spend on each of the elements of the array. And if we work this out from the underlying data, for some value of n, the least squares fit for psum1, as you can see here, the upper line is 368. That's the y-intercept, the processing time to just get going, plus 9 times the number of elements. Whereas psum2 spends the same amount of time getting started up, but then as it gets going, it's showing a much better performance per element of only 6 cycles per element of the input. We can see then that we'd prefer the implementation that leads to psum2. As the number of elements in our array gets larger, we're going to be spending only 2/3 of the time that we would spend on psum1 to do the same calculation. Let's take a look at an extended example that illustrates some ways that we can improve the performance of a particular algorithm by the way that we choose to implement it. And for this example, we're just going to use a simple data structure that stores a vector of values. The individual values are defined by this first type def. We'll see that they're just long elements, and I've defined a type called data underscore t. Again, that underscore t is a convention in C that says this is a type. And then that's going to be used in a structure that has a simple vector representation where the first element contains the length, in other words, the number of elements that are in the vector, and the data itself is going to be a pointer to these data t objects. Under the hood, we would be allocating this at runtime with malloc and mallocing len times size of data t elements and storing the resulting pointer at the star data element in the structure. And then I've defined two new types here, vecrec and vecputter. So a vecrec is one of these structures containing the long and the pointer, and then vecputter is just a pointer to one of those things. And I've illustrated that here in this little simple diagram. The structure itself is this portion. It's got the length value and then a pointer to memory that we've allocated that's going to store the actual values of the vector. And then this would be an array of len elements, each of which is of size data t, so we can store those longs there. Going along with that data structure in our abstract data type, we're going to also add on some functions here. We're not going to look at the implementations of these things, but you can imagine how they would work. It's pretty straightforward. The first thing is going to be new vec. This is kind of our constructor. It's going to allocate the vector structure, which I've reproduced up here. It's going to allocate one of those things, and then it's going to also allocate sufficient memory to store len elements in the vector and store the resulting pointer at this star data element of the structure. So new vec just gets a length. That's going to be stored here. Then we're going to malloc enough memory to store that many longs. We are going to be able to get a particular element out of the vector, so get vec element. This is going to take a pointer to that vector structure. It's going to have an index that's going to index into the data itself, and what it's going to do is fish the value out of that location and store it at the address pointed to by this pointer. We also want to be able to get the length. Obviously, this is just going to basically return the len element of that underlying structure. We give it a vector structure, and it just gives us back the length. And then we're also going to define an ADT function that is going to give us the beginning of the memory that's allocated for the vector itself. So we give this a vector structure, and we get back a pointer to the data that structure refers to. So these two guys are quite similar. One of them is going to give us the value of the length, and the other one is going to give us the value of data. Now what we're going to do with that vector abstract data type is implement a series of successively optimized implementations of a combine operation. And I'm using combine intentionally because we want to be able to either add together the elements of the vector or multiply together the elements of the vector. And in order to make it easier to sort of run these experiments, we'd like to not have to redo the code for each combination of different optimizations and each of those two combination operations. So the way the code's structured here is a little unusual, but it actually makes it easier to do the experiments. What we're going to do here is create some sharp defs that give us a value for the identity value. When we're doing sums, we want to start with 0. When we're doing products, we want to start with 1. And that's what that ident gives us. And then we also want to use different operations. So in the case of the summing, we want to use plus, and in the case of the multiplication, we want to use a star. And we'll see that these are used here in this first version of the combine function, where we're initializing to ident, and then we're using op here as the operation that we're going to perform. You've probably seen this use for sharp defs in the past. This might be sort of a new use of them, but it's completely legitimate. When the preprocessor expands these sharp define definitions, it's just doing a textual substitution. So it doesn't care that this happens to fall into the position of an operator between two variables. It just substitutes in the plus or the star in order to derive the code that's finally handed off to the compiler. So let's look at this combine operation. This is another element of our ADT. It's going to get a vector pointer structure, and it's also going to get a pointer to the data type. that's stored in the vector. So here's where the data live, and this is going to be the location where we're going to store the result of that combination operation, whether it's a sum or a product of all the elements in the underlying vector. We're going to create a counter here called I that's going to be used in a for loop, and in order to get started, we're going to store at that location our identity value. So let's just think about the addition version of this. We're going to initialize this guy to 0 because that's what ident would be defined to, and then we're going to enter the loop. We're going to go from I equals 0 to I is the vector length and increment I each time. We're going to fish out the value from the ith element of the vector using our getVecElement ADT function, and that thing takes the vector structure, an index, and a pointer to the location where we're going to store that value. So this function is going to grab the ith element of vector v and store it at the location defined there because we're giving it the address of that local variable. Having gotten a value out of the vector, then we're going to do our combination operation. So we're going to start with whatever was at the dest pointer, perform that operation on the val. So if this started out as 0 and the first element in our vector was a 5, what we would do is say star dest equals star dest plus 5. And then continue to iterate through that until we run out of elements in the vector. And then when we return from combine 1, the value in this location, which was a pointer supplied to us by our caller, would have the sum, in this case, of all of the elements in the vector. Let's consider now some strategies for optimizing the performance of that combine operation. Here's a new version of it called combine 2 that is going to eliminate an inefficiency in the way that we're doing the looping. If I go back here to combine 1, we can see that inside of every loop of the for statement, I'm calling this function vecLength of v. Now that doesn't seem like a big deal because we know that all that's going to happen there is that we're going to grab the value of the len component of the structure and return that. But that actually incurs the cost of making a procedure call. So we're introducing that procedure call into every single iteration of this for loop. Instead, what we can do, because we know that the length of the vector is not going to change after we enter this function, we can calculate that once and store it in a local variable. Now inside of our for loop, instead of having a function call embedded in each iteration of the loop, we're only going to have to do a lookup of that value, which is probably, because it's stored in a local variable, probably going to be allocated by the compiler to go into a register. That's also likely to be the case for this iterator control variable I, so both I and length are going to be in registers, which means that they're going to be accessed very quickly through each of the iterations, which could be many, many thousands of iterations of this for loop. Here's another example where we're reducing procedure calls further. If we go back and look at the implementation from the previous version, we're calling this getVecElement every time we want to get the value of the ith element of that vector. We can instead make use of this additional function we've got from our ADT. It says getVecStart. You'll recall that this just gives us back the location where the data themselves are being stored. We can then make use of that directly inside of our for loop. So instead, in the previous case of calling this function every time we want to get the value of a datum, we just grab the beginning of it and then refer to the array that contains that data by just doing a simple array index. We know that under the hood this is going to turn into some kind of a load effective address style calculation where we're going to use that really fast hardware to calculate the location and fetch the value of the data at index I. Now this is going to be faster, but it also requires that we have guilty knowledge of the way that this abstract data type is implemented. Now again, if we're focused on performance, that may be okay. We might be willing to pay the price of kind of reaching inside of that ADT and using its internal structure to our advantage. But we're going to materially harm our ability to refactor that vector implementation, to reuse it, to modify it down the road, because if we change the way that the ADT is defined, we're going to have to change everything that uses its internal structure in the rest of our code base. Again, that's the trade-off we're thinking about here. We can optimize this further by using our knowledge of the internals of that ADT, but it might well lead to unmaintainable software going forward. That said, it does result in a performance improvement because we've now replaced a function call in the calculations that it's going to do with a reference to an array. Finally, we can eliminate some unnecessary memory references. Going back here to the previous version, we can see that every time we accumulate the next value from our data, we're doing dereferencing of a pointer a couple of times before we execute the combination operator. Because those are actually memory references, they're pointers, so they can't be allocated in registers, we're going to pay the cost of going out to memory each time we do that. Instead, we can define a local variable that's going to act as our accumulator. We'll initialize it to our identity value, 0 in the case of sum, 1 in the case of multiplication, and then refer to that inside of our loop. We're the same basic operational pattern, but now instead of dereferencing that dest pointer each time through the loop a couple of times, we're actually going to just use that local variable, which again, like I and length, are very likely to be allocated by the compiler as register values, which means that this is going to be incredibly fast. And then to ensure that we're keeping the contract of this combine operation, at the very end, we're going to take that accumulated value and store it at the location pointed to by this dest parameter so that the caller gets the combination that it expects. Let's look at some experimental results here. We've got along the side here the different combine functions that we just looked at and a little summary of what they did. And then addition and multiplication combination for both integer values and floating point values. As you might expect, the floating point performance is just in general slower than the integer performance. Let's just look at one of these data sets. We'll just take a look at the integer addition operation. You can see that the base time here is 10.12 cycles per element. This is just the basic ADT with a little bit of optimization turned on in the compiler. Then we moved the vector length calculation outside the main loop, so that considerably speeds up the iteration each time through, and that reduces our cycles per element to 7 and change. Then the direct data access, this was dereferencing the underlying data pointer and using it directly in the main loop of the sum operation. That basically did not change the performance at all. You can see here in the other examples almost exactly the same. In the integer case here, it shows a slight increase in the number of cycles per element, so it's performing slightly worse. My suspicion is that that might have to do with basically just inaccuracies in the measurement of the performance. It's kind of hard to say exactly what's going on there, but in general, it's not making a huge difference. It might also have to do with the way that the values are being cached, or perhaps the overhead of the function call into that data access function was not as considerable as we imagined it would have been compared to the amount of time necessary to access the data from cache or from memory. And then finally, where we substituted in a local variable that was probably allocated to a register for the memory reference to the return value, we get perhaps our best improvement overall. It's almost 7 times faster in the case between combine 3 and combine 4, and almost 10 times faster than the base case for integer addition. And you can see that that result is fairly consistent across the board. We get quite a dramatic improvement in performance by just using a local variable to accumulate our results. So you can see here the claim that I made at the beginning of this presentation that we could get a 10-for-1 improvement in performance by just monkeying with the specifics of how we implement the algorithm bears out to be true. And this is not an unusual kind of a performance improvement. It's still not going to be as good as using a better algorithm that has a better big O complexity, but within the constraints of a particular kind of algorithm, you can see here quite clearly that we're able to improve the performance quite dramatically within the confines of the overall algorithmic complexity. I also wanted to point out that I've included the assembly language for these various versions of the combine operations. So if you want to read through these in the handouts, that would probably be instructive so you can see how the compiler is changing its output based on the way that we're revamping the implementation of this combine operation.